This morning, I hope to give you a little bit of a tour around Tinkercad, whether you are familiar and have used Tinkercad before. I hope you might find something new, and if you're completely new to it, then it will be fine. It's a super little piece of software, and I hope to be able to show you how we can combine some of the national curriculum learning from computer science and from design and T into a very kind of practical outcome, really. What is Tinkercad? If you've not had an opportunity or any time to have a look at Tinkercad, it's a super piece of software. It's cloud-based. It's free, and I often say there's not much in life for free, but I think this is well worth the money. It really is excellent. It's a great introduction to CAD, computer-aided design for pupils. A few years ago now, it was bought by the Autodesk suite, and as such, as it's been developed, it's been aligned to the Fusion 360 suite, which is more familiar to Key Stage 4-5 pupils, certainly in DT. But one of the great things for me about Tinkercad is this concept of building solid geometry shapes. So from a maths point of view, we're able to introduce solid geometry, so cubes, cylinders, spheres, cones, the concept of prisms. And the whole premise that Tinkercad is built on is being able to combine solid shapes to create new shapes. And as we'll see, those shapes could be solid, or they could be a whole. And when we start combining them together, we're able to make some fairly detailed, interesting shapes, as I hope we'll see this morning. So what we're going to take a look at in particular is this code block feature that will allow us to use and introduce some of the computer science concepts into our design. So I'm just going to run through some DFE content here. Don't need to concentrate on this at all, but I've got some programmer study from design technology at Key Stage 2, and the next slide we'll take a quick look at the computing programs of study. I could have highlighted many of those words on there, but one of the key words in the world of design and technology now is iteration and iterative design. This concept of being able to quite literally tinker, the concept that Dyson introduced a few years ago in the design world in terms of iterative design and how a design is improved and tinkered and modeled, and prototyping. And prototyping from a DT point of view is producing something that we can look at, evaluate, doesn't necessarily need to be a fully finished modeling, and we can produce those prototypes through computer-aided design, which is what Tinkercad would allow us to do. So to just have a look at some of the computer programs terminology there, a great being able to combine maths and DT through this computing. We will look at some sequencing, repetition, variables, and actually using some software which is free. So Tinkercad, as I've said, it is free, it's cloud-based. Kids can use it at home. They can use it on machines at school. It doesn't need heavy, intense programs sat on servers. It's worth spending a little bit of time at the outset if you're going to use Tinkercad in school, setting it up right so that you create an account as a teacher that then enables you to create a classroom where the children can store their work, you can see their work online. You can set up an account for yourself to play with. There's a really big library of projects that you can access. There's lots of teaching resources online there for Tinkercad lessons that you can use. There's an hour of code a day module, one of which I've kind of adapted here. But it's worth, as I say, just making sure that you get it set up right in the first instance, so that you can then set your classrooms up. It's quite difficult to go back and to reset an account. So code blocks, once you're into Tinkercad and up here on the top left hand side, there's an option for you to select code blocks, which is new, sorry, from the drop down menu, and you'll be presented with a window that you can see there on the right hand side. So if your pupils have been using Scratch, they will be quite familiar with the concept here of visual language and drag and drop. And essentially what we have now is a 3D modeling workspace, basically. So there's three areas to the window. We've got the blocks panel, which you can scroll up and down, and we'll see that working in action this morning. And they're color coded like they are on Scratch. So you've got shapes, modify, control. There's a maths function that we'll have a look at as well, and a data function. You drag the blocks from the panel into the blocks editor, that bigger square in the middle. And as you do that, and you click on the play arrow up to the left of, to the right, sorry, of speed, you can then see block by block what's happening in real time. There's a couple of little mouse control functions on there. So Tinkercad, like most CAD packages, it's better with a mouse and a scrolly mouse rather than the trackpad. But with a mouse, it allows you to zoom in and out of that 3D viewer, and by holding down the shift key, you can pan around that window as well as. So when we come on to wanting to create forms, we've got three little blocks that we've dragged across there now. So we've added this cylinder, and sorry, let me just show you. When you have these blocks in the window here, and you click on this arrow to the right, it will expand the this whole command, so that we then have control over the, in this instance, the cylinder, the radius, the height, and the number of sides. So in this instance, the first cylinder has been highlighted as a solid shape. The second cylinder has been designated a hole, and we've made that hole a radius 40 as opposed to a radius 50, and then we've created a group by adding these two bits together. So when you are doing this live, you can see what's happening in the 3D viewer step by step, and you can either do it step by step at your own pace, or you can play and it will do it automatically for you. So all being well now, I'm going to show you a little video of exactly what we've just seen on the screen there. So you drag and drop across, you open that dialog box, you can put your own parameters in. And if you click on that play button up there, you've seen in real time what's happened. We drag another block, we've made it a hole. And what you will see in Tinkercad is you'll get this grey effect over the top. And it's not until we create them and select them as a group that we actually get that hole appearing. So very, very quickly, we're able to create shapes and forms. We can change the parameters very quickly in real time. And children are able to see that happening really very, very quickly. We can introduce a variable concept here. So from a computing point of view, variables are one of those key concepts that we need to introduce pupils to, and it's this concept of essentially a number, a piece of information that we store somewhere, and in teaching that we would have talked to them about scoring a game or the number of cars in a car park. And in this instance, we'll see another little sort of clip unwind in a minute. We just drag and drop a variable across. We've defined it, we've called it the radius, and at this point we store that number 35, which will be millimeters in this instance in that variable. Now, the other great thing about Tinkercad is that we can also use mathematical functions. And so we can drag across little operations, and you can use your variables to put in there. So in this instance, we have created a variable called radius. I've put a value in there of 35. I've taken the radius and put it into one of my mathematical operations. From the drop-down menu, I've taken the subtract function, and I've put 3 in there. So as this bottom bullet point here starts to kind of explain now, and you might use the prim concept, and we'll come on to that a bit later, is you can start to sort of ask your pupils, what do you think is going to happen here now? And one would hope that we'll have an answer something like, regardless or however big that variable is, in this instance 35, the hole that we have created in the middle will be the original radius minus 3 millimeters. So what we will end up with, and I hope you will see this little bracelet bangle unfold this morning as we go through this session. What we have now created is essentially a hoop, a bangle of a radius, which is a variable, and it will have a wall thickness of 3 millimeters. So regardless, however big that bracelet is, that radius in the first instance, our wall thickness will always be 3 millimeters. So we will see this little function unwind now. So we take the variable up, a right mouse click down on that item. Now every time you bring a variable in, it calls it item, but you need to rename it. We're going to put 35 in there as our value, and all we're going to do now is just substitute that radius into those 2 commands. And now when we play that, we will see that little process. If you actually play step by step, you will see a bit like Scratch, the steps happening stage by stage. So I'm just going to play that again, because I'm not always quick to pick things up. And obviously, one of the great features here to be able to sort of get pupils to play with is go back, change that variable. I think we changed it from 35 to 80 in this instance. And you can see in real time, the impact, the effect of that going on in the 3D window viewer. So we take the radius into that little mathematics operation, take away -3, and now play it. We change the variable up at the top, I think to 80. We'll get a bigger hoop, but we've still got that 3mm radius there. So we've created a little bangle with 4 little blocks, but we have a variable in there and a little mathematics operation. Well, we can start to get a little bit creative now, and we can create shapes, and in this instance we're going to create a little love heart that will run around the circumference of the bangle. So we're going to introduce a few new features here. We're going to create a new object, and we're going to call that object heart. In the same way that we added cylinders before, we're going to add this heart, but we're going to make it a hole, and we can see that by this being selected. Only because I've played with this a little while, I've scaled the heart to 0.25, and I've left it on the Z-axis as 1. And I'm going to rotate it on the X-axis by -90 degrees. And then on the bottom block, I'm going to move it, and I'm going to move it on the Y-axis to the radius. Here's that variable again. So whether it's 80mm or 5mm or 35mm, it will always move this love heart out to the right space. 1 or 2 people might be asking why we've rotated it -90 there. I'd like you to have a little think about that, and we'll come back to that later on when we see the final product. So we'll see this now in operation here. What I didn't do the first time was I didn't create an object when I made that bracelet, so I've been able to go back and we created an object, the bracelet. Here we're creating this heart. So we drag and drop these shapes across, turn it into a hole. What you can get your pupils to do is if they drag that in and it's of a scale factor 111, and then they actually play the video, the little 3D viewer, they will see that the heart is far too big, and so they can come back, they can go to 0.5, run it again. It's great in terms of its speed, its interactivity, and this kind of real-time processing. So here we go, we've brought the heart in, we've rotated it, we've moved it out to the radius, and there it is, it's parked. We've put 1 heart in there, and it's now parked. What we really want to do is we want to be able to rotate that heart around the circumference of the bangle, rotating it around the center point. So what we can do here is we can introduce the concept of some loops and counts. Now this is a little bit, it starts to get a little bit tricky here, and it would be one of the options here is how you might scaffold this or present it to children in your group. What I will do with Will after this session is finished, I will send Will a link to this piece of code that you will be able to find on Tinkercad. And once you've then got an account, you can you can tinker this. It's effectively downloading it, so you can tinker it. You can then put it into your own classroom, and you can scaffold it. So you can take the variables out. You can remove bits in. You can create a sort of 2 or 3 level approach, so that for your more able students, you can get them to think about some of these counting operations, and for some of the less able, you can just leave it in there and allow them to play with the variables. So what we're going to do here is we're going to look at this concept of some counting. Now, in a similar way to Scratch, when you've got these count loops, we need some sort of reference there. So in this instance, when you start from new here and you drag the count loop in, the first time it defaults to count with I, and that's fine. The more counts you introduce, it will go JK and so on, and you can just change those yourself. But what we're going to do here is run a little bit of a video simulation, and then I'll come back and I'll explain, or I'll try to explain some of this as we go through what's happening live. So we create this new variable, and I think we call it number of holes. There should be a space in there between number of holes. And this now means I'm going to rotate that love heart 6 times around the center. So we're going to create this new object called pattern. We're going to introduce the count feature. So we're going to count from 0 because we've got 1 hole there already. And we're going to introduce a little mathematical operation here. So we're going to take our variable and we're going to do -1 because we've got 1 hole there already. Now we're going to introduce the shape. So we need to add a copy of this object, and in this instance it's the heart. So it now sees that heart as a standalone component, and we're going to rotate around the z-axis. It's a great opportunity for the pupils to find out, well, if they don't select the z-axis and they select the y-axis or the x-axis, it will just rotate the shape in a different orientation. So this little sum here is taking the first, the second, the third hole, multiplies it by 360, and then divides it by the number of holes, so that we know which heart it is that it is adding. This is the final sort of few steps at the bottom here, and as I say, this code will be available from the URL link that I'll send Will. Once you finish this, you need to add a copy of the bracelet, which we've done there, and then you delete the heart and the bracelet. So now when we run that, we'll see the heart added. We'll now add another heart, rotate it, and so on and so on. Now it will add the bracelet, delete the heart, delete the bracelet, and there's our bracelet with 6 hearts. You could change the variable. In this instance, we've done 10. So it now will put 10 hearts. So this little sum that it's running through is taking the third times 360 divided by 10. So it's working out the number of degrees by which to rotate it. You can change the radius here. You can actually speed up the simulation here as well. But we've now made a bracelet 40 radius with 20 holes. So the children can play till their heart's content. So there we are. There's that finished bracelet. This little concept here might take a little bit of time to get an understanding around, but I'll put the code up there for you to be able to take a look at and tinker. For me, I've kind of my background is manufacture, engineering, electronics, and I love making things. And one of the great for me, I kind of my bent is physical computing, and I love tinkering and making. And one of the great things about this Tinkercad is being able to actually manufacture from it. And so once you've finished, you can actually export your designs. So you can export them for 3D printing. If it's a 3D object, you can actually export files for cutting on a laser. But we're going to export this for 3D printing. So we just export in a .stl file. STL, standard tessellation language. It's a language that 3D printers understand. It converts it into G codes that drive the machine. So it's a little bit of post-processing here, but I've done this with year 7s who have kind of just eaten this up, and once they see it, they're in at lunchtime sort of knocking these things out, and they've had a little stall at the Christmas fair. Cura is a free piece of software. It does need a download, but once you've exported your STL file, you import it into Cura for slicing, which is this a screenshot that you've got here, and it will give you a little bit of information down here, and it's showing that this this bracelet on the settings that I have running on my machine will take 1 hour and a quarter to print, and it will use 9 grams of PLA filament, which equates to about 14 pence or there or thereabouts. So with a little bit of a few clicks, quite literally, you don't need to do anything. We're able to export this file, and we can then transfer it on our SD card onto our 3D printer. This comes with a little bit of a health and safety warning here, because I did this on a 1 second time-lapse film on my phone, and it took 1 hour and a quarter to print, and therefore the bit here that you can see that's called Ender with the dragon moves quite quickly at the start and at the end of the video, because it's laying down the PLA filament. In layman's terms, this 3D printer is 3 servo motors with, in effect, a hot glue gun that is melting a PLA filament through a very small nozzle, and it melts, and as the 3 stepper motors move in tandem, we will end up with a 3D printed object. So let's just be prepared. As I say, it moves quite fast to start with, but it shows the printing of the product. There we are. Someone did say to me it would be great if we could 3D print in this at this speed. so this is where it slows down a bit now, because it's actually it's not printing the holes. It's clear it simply prints to create the holes. And there we are. Now, I know we don't have open mics on here, but I hope you might now be able to look at that little bracelet. That's 70 millimeters in diameter. I hope you might be able to look at that now and think about why I rotated the love heart minus 90 degrees as opposed to 90 degrees. And as teachers, we're great at answering our own questions. So if you've been able to have a little bit of a think about that, one of the ways to explain to children in the class and to show them why I rotated that minus 90 as opposed to 90, I hope you'll see that where the love heart dips in at the bottom to create that little dimple effect. If we didn't rotate it minus 90 and we rotated it just 90, then you would have this little dimple bit hanging in free space. And the best way to try to get them to understand that or to see that is to give them some Lego bricks and get them to try to make that love heart in Lego bricks if you'd rotated it at 90 degrees, and you can't build that little dimple without having some sort of scaffold or support in there. Now, it is possible when you 3D print to put a lightweight scaffold structure in there, but it means you've then got to unpick it afterwards. And it is just so much easier in this instance to rotate the love heart minus 90 and to print it that way. So as we come towards the end here, we mentioned PRIM, this little acronym that we use with some of our students, where we get them to predict, run, investigate, modify, and make. A little bit of think time here. I've got a piece of code here on the screen, and it's not all there because I couldn't fit it on, but just a little bit of an opportunity for us to think about what that might look like. We can see we've got 3 variables up at the top. The first kind of object, create object up here, sort of gives it away, create a bangle. But we're now going to create some indents and some patterns and some indents. And you could give this to students and ask them to have a think, and all being well, they're not going to come up with a kind of gear tooth looking wheel, but if you use this PRIM model with the code that we'll paste and share with you afterwards, you would be able to get them to do some PRIM. And there's another couple of examples here. The third one in a minute will be a bit more interesting, a bit easier for children to see. So here I've got 3 examples of some code. This one here is the textured bangle. As you can see, it's named up here. So I'm going to run this and we'll see it unfold. And then there's a second little object, and there's a third object. And all I've done here is just I've moved that slider across the top to speed up things. So we're introducing the same shape here, and I've just put it on a slight angle and rotated it and group it, and then we repeat that again, and we just rotate it in the opposite direction, spin it around, and we create a kind of a bit more of a textured bangle. Here's another little example. This one is off of the Hour of Code on Tinkercad, and it's a lovely little example of code blocks. This actually takes one of the downsides of 3D printing is it takes quite a long time, but this is a little tea light holder, not for use with a naked flame, but you can put the little battery flames in, the little battery powered things in there. But that tea light takes about 4 hours to print. And this is another example off of the Hour of Code, where you can make snowflakes. It's a great little activity at Christmas. I've always no two snowflakes are the same, and when kids make paper snowflakes at Christmas, why not get them on a bit of code? Give them the code, let them tinker with it, and as they change the variables on there, they'll create their own unique snowflakes. And they are taking, if you want to print those, they are taking about 40 minutes to print. So I'm just going to put the final slide up, which sort of brings things to an end. The slightly ghosted image there are some photographs on the bed of the 3D printer. So we've got the orange textured bangle there. We've got that candle tea light holder with a little battery powered candle in there, and one of the snowflakes. So I hope that you might feel kind of inspired by that, and you might think that your children in your schools, be it in a computing or a DT lesson or in a club at lunchtime, that might be something that you can explore with them. The one thing I'll say about that 3D printer, you know, that 3D printers have evolved quite a lot. The first 3D printer I bought in a school was over £3,000, and it had a dual filament. It had 2 filaments in it, and I look back at that now and I think, whoa. The 3D printer that I've used there was £220, and that's within the realms of a purchase by the PTA, really. And if you've got any links with your PTA or parents that are into manufacturing or local companies or somebody that might just want to buy and support and buy that for you, I think at £220 these days, it's a real snip. It's unrivaled for me. If you print with PLA, you don't need any extraction. The filament is £17 a roll, but that bangle that you saw print was about 14p. So I think it's a real kind of inspiring, creative, iterative opportunity to combine a bit of computer science with design and technology in a real fun way. So thank you for attending today and listening, and I hope that you may have something of a takeaway today, and I'll get that link to that love heart bracelet that we'll be able to share with you later. I'll take some questions via Will, if there are any in there.
Yeah, we've got a couple of questions here, Barry. Thank you very much for that presentation. It was really, really interesting. Yeah, we've got a few questions I'll read out now. First of all, Barry, have you had any experience with BlocksCAD?
No, I have seen it, and it's one of those things that I you know, is on the sort of to-do list, really. is to have a look at that as well as. But I'm assuming it's fairly similar, I think.
Yeah, we had a question asking if you could explain the differences between the two, but I guess if you haven't experienced it,
No.
we can't answer that one just yet. You've already suggested some places to get tutorials from. That was another question.
Yeah.
On the Tinkercad website, there is a link under the teaching tab. There is a link to several resources. Hour of Code was one of them that had some stuff there, which is great.
Yeah.
Somebody's asked.
The other thing, sorry, Will. In terms of that, YouTube is an amazing sort of resource bank of tutorials, be it kind of introduction to Tinkercad if you want to use it as a 3D modeling in DT or just as a 3D modeling, or whether you want to use code blocks. Tinkercad have actually put out quite a good resource bank themselves, and for teachers with some lesson plans on there as well. So there are some lesson plans that overlap science, they overlap some geography work. There's a huge amount of resource out there to support Tinkercad.
Brilliant. And do you know what the programming language is behind the blocks in Tinkercad?
I don't. That's a very, very good question. I would imagine there's an element of JavaScript behind there, because you can kind of break out, or you can import some JavaScript in. So I would imagine there's a fairly substantial amount of JavaScript behind that.
Okay. And somebody's asked, can you repeat the name of the printer that you used?
Yeah, so this is an Ender. It's a Creality printer, and I bought this one to play around with at home just before lockdown, and I bought this in February, and I managed to get it at just under £200. And then with the explosion of kind of maker space, hack spaces, schools, all sorts of mini kind of enterprise people sort of set up to 3D print these, the PPE visor shields. I did quite a few of them locally. They kind of sold out. They disappeared, and PETG, which was a more appropriate filament to print the mask visors from, sold out, because you can clean PETG with an alcohol-based meth spirit or something like that. So it was much safer from a PPE point of view. You couldn't get it at all. The Crealities, this Ender, they are now back in stock. Have a look online. I'm not going to plug any particular company. I'm not into that. And various companies sell them, but do some work and dig around and buy the cheapest one you can. They are now around the 220 mark. You don't need to buy the auto bed leveling system. They're fairly easy to set up. In actual fact, you go to YouTube and you can follow the assembly instructions, load in the filament, swap in filaments. It's all on YouTube in terms of how to do. But they're around the 220 mark